Hey everyone, my name is Josh Go and I'm joined by my brother Sam Go. In this SAT Subject Test Mathematics Level 2 module, we will be going over select topics from the exam and go over 30 sample questions that we picked from sample tests. And the types of questions that we chose are according to the breakdown provided by the College Board. The breakdown is as follows. Numbers and operations make up 10 to 14% of the test. Algebra and functions make up 48 to 52% of the test. Geometry and measurement make up 48 to 52% of the test. And data analysis, statistics, and probability make up the last 8 to 12% of the exam. Without further ado, let's begin. All right, let's start with number and operations. So first we have PEMDAS, our order of operations. P stands for parentheses. E stands for exponents. This is followed by multiplication or division, whichever one comes first, reading left to right. And it's followed by, same thing, addition and subtraction, whichever comes first, reading left to right. Next, we have prime factorization. That's essentially decomposing a number into its prime factors. This also applies to just regular factorization, where you just decompose a number, but not into its prime factors. Let's say we have 120. Let's try to do the prime factorization of that. We can divide that up into 2 and 60. 60 can be divided up into 2 and 30. 30 can go 2 and 15. 15 can go 3 and 5. So thus our prime factors are 2, 2, 2, 3, and 5. And we can verify that all these are prime numbers. Okay, moving on to complex numbers. Complex numbers are in the form a plus bi. They always have a real part. It could be 0, but it also has a imaginary part. So imaginary numbers are defined as the square root of -1. So this is I to the first power, right? So you'll see there's also I to a certain power in the test. We have I squared, which just gets rid of this square root sign, so we have I squared equals -1. Continuing that pattern, we have I cubed equals -I, and then I to the fourth equals +1. And note that as this cycle keeps going, we can extend these exponents into the other powers. This one would correspond to I to the fifth. This one would correspond to I to the sixth. This one to I to the seventh. This one to I to the eighth. And the same process continues for the higher powers. So we can also graph these complex numbers on a graph. We have our x-axis as our real axis, and we have our y-axis as our imaginary axis. So let's take the example. We'll just make up something in a plus bi form. Let's have 1 plus 2i. So in that case, we move 1 unit to the right on the real axis, 1, and then we move up 2i units on the y-axis. So this is labeled 1i and 2i. So then our point would be here. Moving on. So let's quickly do a refresher of our exponential rules. We have rule 1, where we have a base raised to an exponent times the same base raised to another exponent, and that equals x raised to the addition of both those exponents. Rule 2 is like the opposite of this, where we have a base raised to an exponent divided by the same base raised to a different exponent, and that's the same thing as the base raised to the difference of the exponents. So next we have 1 over the exponent, and that's the same thing as saying the exponent raised to the negative exponent. Rule 4, we have a exponent raised to another power, and that's the same thing as saying it's the base raised to the product, or just multiply both of those powers. Rule 5, we have 2 numbers raised to a power, and that's the same thing. We can break it down into that first number raised to that power times the second number raised to that power. Rule 6 is our identity type rule, and that's just saying any number raised to the 0 power is 1. And rule 7, we have 2 numbers that are square rooted, And you can break that down into the square root of the first number times the square root of the second number, because this is the same thing as saying x, y, both raised to the 1/2 power, and we can refer to Rule 5, and that's how we break it down. Okay, moving on to Venn diagrams. I just wanted to cover that if we're given a total, I'll call it T, and we're given a amount B for blue, R for red, and an intersection area of X, that this would be modeled by the total equaling blue plus red minus X. Now, you may be asking, why is it minus X? Well, blue covers this entire portion, including that X, right? And red covers that as well. So we're basically double counting that X portion, right? That intersection point, intersection area. So we have to remove it once just to account for that. All right, moving on. When we have matrices, we can add them together as long as they have the same dimensions. Let's say I have two 2x2 matrices with numbers A, B, C, D, and we're adding it to that second matrix with numbers E, F, G, and H. Here we just add corresponding numbers. So this first item would be A plus E, and we can do the same for the rest. B plus F, C plus G, and D plus H. When we're multiplying, we can get two situations. The first one is where we're multiplying the matrix just by a number. This is called scalar multiplication. In that case, we just multiply that, that scalar to each of the members. So we get 2a, 2b, 2c, and 2d. Now we can also get the situation where we're multiplying two matrices together. And this is called a dot product. And in this case, for this first item, what that would be is we'd have to look at the, let me change colors here. We have to look at the first row of the first matrix and look at the first column of the second matrix. And this term would have to be A times E plus B times G. And we can do the same thing for, let's say, the second term, or the second item, where we have to look at the first row and the second column. So that would be A times F plus B times H. And we can do the same thing for the last two. I'll just do it really quickly. For this one, we have the second row of the first matrix, and then the first column of the second matrix. So that would be C times E plus D times G. Same thing for that last one. Let me change colors once more to navy. There we go. And that would be that second row of the first matrix times the second column of the second matrix. And that would be C times F plus D times H. Finally, we have something called the determinant. I'll just do it for the 2x2 matrix. When taking the determinant of a 2x2 matrix, we have AD minus CB. So that's when you have a matrix that looks like this. So essentially, we're just multiplying these two terms and subtracting it by these two terms, multiplied together. All right, moving on to sequences. In regards to sequences, we have two types. We have an arithmetic sequence, where it's basically just adding a number to the previous number in the sequence. So it would, let's say we have 1. If we add 2 to that previous number, we get 3, and we can continue 5, 7, 9. So if adding is for an arithmetic sequence, then multiplying is for a geometric sequence. So that would look like 1, 3, 9, 27. That's what that would look like. And the formulas are right up here. Alrighty, so now we're moving on to series. And all series is basically taking the sum of all the elements in a sequence. So we have the two types, arithmetic and geometric. With arithmetic series, we can only take the finite sum, so it ends at a nth element. So its formula is n over 2 times a sub 1, which is our first element, plus a sub n, which is our nth element. So we also have geometric series, and we also have a finite sum, so this again ends on an element, equals a sub 1, which is our first element, times 1 minus r to the nth power. And remember, r is our ratio over 1 minus r. R is our ratio between two elements, right? So we also have a special case for geometric series, which is an infinite geometric series. And in that case, r has to be less than 1, because it has to converge, right? So let me label this infinite. And that formula is s equals a sub 1 over 1 minus r. We can see the similarity between our infinite series and our geometric series, because if our r to the infinity, like it's a fraction and you're raising it to a power of a really high power, it's going to converge to 0. And in that case, this term would turn to 1. And that's how we get our formula over here. All right, moving on to vectors. In vectors, we have, this is a vector. It has both a magnitude and a direction. When we add vectors, let's say we're adding this vector to this vector, we use the tip-to-tail method. So essentially what we're doing is taking this and and putting it at the tip of that previous vector. And then our resulting vector is this. In addition, we can take the components of, we can split up the vector into its components, its x and y components, this x component and the y component. And our y would be m sine theta, with m being our magnitude, and our x component would be m cosine theta. All right, moving on. For number 1, we have each term of a sequence after the first is inversely proportional to the term preceding it. If the first two terms are 2 and 6, what is the 12th term? All right, so what does it mean for something to be inversely proportional to the term preceding it? Well, we know 1 over x is an inverse relationship, and we can multiply that by some constant k. So in this case, x is our preceding term, and k is some constant. And this equals our next term. So let's see how this works with what they've given us, our 2 and 6. So let's look at our second term, right? So 6 is our next term. And let's use this relationship. So that equals 1 over the preceding term times some constant k. And now, multiplying 2 on both sides, we find that constant k. K equals 12. And this constant is going to be the same. This rule follows with all the subsequent terms. So let's try to find the third term, right? Now the third term, we don't know what it is, equals 1 over, we're using this same relationship here, this same relationship, is 1 over 6, which is the preceding term in this case, times our constant 12. So this third term equals 12 over 6, which is 2. Now if we continue this pattern, let's find the fourth term, equals 1 over 2 now. we're using the same thing, same equation that we have here, times k, which is 12, and we get 6. So we see this repeating pattern. It goes 2, 6, 2, 6. Now, what does that tell us? That tells us all the odd terms are 2, and all the even terms are 6. If it's asking us what the 12th term is, it must be 6. Question 2 asks, if the two solutions of x squared minus 9x plus c equals 0 are complex conjugates, which of the following describes all possible values of c? Well, it tells us we have 2 complex roots. That tells us that the discriminant, b squared minus 4ac, has to be less than 0. And just as a reminder, that if the two solutions were real, that would mean that the discriminant would be greater than 0. And if there was only one real solution or one real root, b squared minus 4ac would be equal to 0. But in this case, we have this. So what does that look like? So with an upwards facing parabola, it would look like this, right? The parabola would have to be above the x-axis. So we can go about this 2 ways. We can either plug in our coefficients here into our discriminant equation, or we can graph it out on our calculators. I'll quickly show that here. If we were to graph this out on our calculators, we'd get something that looks like this. If we were to set c equal to 0. So this is x squared minus 9x. So looking at this graph from our calculator, we see that all we would have to do to get this parabola up so that it's not, so it's above the x-axis, right there, is that we'd have to shift it by a number that's greater than this amount right here, which is the parabola's minimum. So just by plugging it in, plugging this all in your calculator, and then trying to analyze the graph and get that minimum, it tells us that the minimum is 20.25. And we know that that we'd have to shift that c, so the amount that we're shifting it by, has to be greater than this amount. So in this case, c is greater than 20.25. In the same manner, if we were to do it this way with our b squared minus 4ac is less than 0, we can plug in our coefficients. B squared is negative 9 squared, which is 81, positive 81, minus 4, A is 1, and C is the value we're looking for. Then subtract 81 on both sides, we get minus 4C is less than negative 81. Divide both sides by negative 4. And we get C, now we're flipping the signs because we're dividing by a negative, is greater than 81 over 4. And 81 over 4 is also 20.25. And we see that our C is greater than 81 over 4. Answer choice D. All right, so number 3, we have if 4.05 to the p power equals 5.25 to the q power, what is the value of p over q? All right, so we have 4.05 raised to a power. That means we can convert this into a log. We can do it a log base 4.05 of, and we know that the solution is 5.25 to the q, so you can add that here, 5.25 to the q, and that equals p. And that's the basic conversion from something to a power to our logs. All right, so we know that if we have an exponent in our log, we can really just bring that outside the log and have it as a coefficient. These are just basic log rules that will be gone over in the algebra section. So q log base 4.05 of 5.25 equals p. And put simply, we can just divide q on both sides to get p over q equals log base 4.05 5.25. And what we can do here is just plug this in our calculators. And that gives us a P over Q value of 1.185. And the value closest to that is answer choice C. You can even convert this value, if need be, to log base 10 if you want to, but if you can input a log base, a custom base for your log on your calculator, you should do so.
Okay, now we're going to review algebra and functions. Okay, so we're going to start with a little bit of a review like we did before. First talking about domain range, asymptotes, even and odd functions, and inverse functions. So let's start with domain and range. These are kind of the fundamental building block concepts. Okay, so usually we have a function, okay? Usually takes an input, we'll call it x. We'll call the function f of x some sort of machine, right? And it spits out y. And usually we see this written as y equals f of x, right? Y is some function of x. It operates on x, okay? So what the domain is, okay? The domain is the set of all x's, okay, that are possible, okay? So sometimes, you know, it might be all real numbers. You can, if you're thinking of a 2D graph, for instance, an xy axis, it might be everything from negative infinity to infinity, but there's some exceptions. We'll see more in the asymptotes below, where a certain number might not be included in the domain. So we'll talk about that in a second. Okay. The range, okay, the range is directly related to that. The range is the set of all y's that are possible, okay, given whatever that function is. It is important to note for a function, okay, there has to be this one-to-one mapping. 1x, okay, we'll call it 1x, will map to one y value only. You cannot have 1x mapped to, sorry, you cannot have 1x mapped to two different y values. Yeah, that does not make sense. That would look like this, for instance, right? If this is the xy axis, if you had x equals 2, okay, x equals 2 here, you can't have it map to this point here and this point, two different y values. It's not a function, okay? Now let's talk about asymptotes. There's another example in one of the coming slides for this, but let's pretend we had some function, y equals 1 over x. Very simple, right? 1 over x. Now, if you graph that, you'll get something that looks like this. I'll do it in blue. Something like this, okay? And you'll realize x can never be 0, right? It kind of, you see these blue lines kind of going off into the distance, but they never quite touch the y-axis, and same with this line as it keeps going up. Likewise, with this line kind of approaching the y-axis, they'll never actually touch. Now here's why, okay? That's what an asymptote is, by the way. This dotted line I'm drawing here at x equals 0, okay? That's an asymptote. Just means the graph kind of starts to approach it, but never quite touches it. Now we can quickly talk about why x equals 0 is an asymptote here. If you plugged in x equals 0 here, you will get y equals 1 over 0, okay? That is an indeterminate form, right? Or actually, more accurately stated, this is undefined. Okay, so I'll bring back my red pen here. This is undefined. Okay, so in that sense, x can be anything else but 0. Okay, so that means in the domain, okay, the domain can be everything but 0. And that's why we have an asymptote there. Okay, so that's just wanted to show what the behavior of when you're excluding something from a domain is, and it ends up in an asymptote just like this. Okay. Now in the top right, we're going to talk about even and odd functions really quickly. Okay. In its most simplest form, okay, an even function is where you take f of x, okay, it will equal f of negative x. Okay, Now an odd function behaves slightly differently. An odd function is where you take f of negative x, okay, that will equal negative f of x. Okay, let's just see what these sort of mean. Let's see if we can kind of make sense of them, right? So let's say we had this here, okay, and it was a parabola that looked like this. Okay, not very well drawn. Let's pretend it was very symmetric. Sorry for that straight line. So in this case, let's say we have, it's just x squared, right? If we have the point 2, we'll have the point 4 up here, and if we have the point negative 2, we'll still have the point 4 up here, right? Because that's just x squared. That's an even function, right? Because f of x, so let's say f of 2 is equal to 4, is the same as f of negative x, or negative 2, right? F of negative 2, and that's still 4. Common property, of course, is just, when you look at it from a graphical standpoint, we have symmetry in the y-axis. So we can kind of note that. Symmetry, y-axis. Okay. An odd function behaves a little bit differently. Okay. So let's do this here, and let's draw a function like this. Okay. This is x cubed. Now, why is this an odd function? Let's mark a couple points again. Let's take that point 2 that we have, right? So 2 will go to 8, because it's 2 cubed. Negative 2 times negative 2 times negative 2 is actually negative 8. That's going to be down here. So that matches the definition here that we have for an odd function. F of negative x, okay, so f of negative 2, let's say x equals 2, f of negative 2 is negative 8, equals negative f of x. F of x, f of 2 is 8, negative 8 equals negative 8. Okay, so that's just the distinction between an even and an odd function. And finally, we move on to what an inverse function is, okay? Inverse function. So I'll kind of draw it in a pictorial fashion first to kind of understand what we're getting at. We drew before this function machine, right? Where you put an x into this function f, and it spits out y. The idea of an inverse function is if you have the y and you want it to get back x, you want to go the other way, you want to invert it, okay? We'll call this one f with a -1 superscript, okay? And here we would plug in the y and get back the x, which is really cool. It's very easy actually to solve for something like this. Let's just say we had y equals, let's say, x squared plus 1, okay? All you have to do is switch the variables. So first switch the variables, x equals y squared plus 1, and then solve for y. Okay, so that would be y squared equals x minus 1 and square rooted. Okay, square rooted. That eliminates the 2 and the square root, and we get y equals square root of x plus 1, x minus 1. So let's see if that works really quickly. Let's say I plugged in 2 into here, into x. Okay, what would y be? 2 squared is 4 plus 1 is 5, right? So y would equal 5. Let's say now I had 5. Will it get me back to 2 if I use this one here, this y equals square root of x minus 1? Well, so far it's looking good because x minus 1, 5, in our case we're plugging in 5, right? 5 minus 1 is 4, and the square root of 4 is 2, and that gets us back our original answer. So that's what an inverse function is. All right, now we'll have a brief word on composite functions. You might see this in a couple ways. But a composite function is basically taking two functions and somehow putting the output of one into the input of the other. Here's what we mean. You might see it in this way. You might see f of g of x. You might also see f and then this little o g, kind of like that, okay? This is basically saying take the output of g of x, right, and put it into the function f. Let's do a couple quick example here. Right, quick example. Let's say f is equal to, or f of x, we'll say f of x, make it simple, is equal to x plus 1. Now write this next one in green. G of x equals, let's say x squared. Let's just leave it at that, yeah, x squared. What does this mean now if we said, or if we were being asked, what is f of g of x? Okay. Now this tells us we're basically putting the function g of x into, or the output of the function of g of x into the input for f of x, okay? So if we now have f of g of x is x squared, right? That's the answer. It's g of x equals x squared. So we're effectively doing f of x squared equals what? Okay. Well, f of x is x plus 1. That means anytime we see an x, whatever's in this parentheses, right, we replace it in the formula, in the x. So we won't just have x plus 1 here, right? This has to now be put in as an input into the function. So this will be x squared plus 1. So that's all really there is to it for composite functions. It's kind of this pattern matching, okay? Now let's talk about transformations. The best way to do this is to probably just draw a quick graph and show maybe a parabola. Here's a original parabola. Okay, so black, in the black pen is the original parabola. Let's just say that's x squared plus 1, okay? Because it's the vertex here is at plus 1. Now, there's a couple ways to transform or translate these sort of shapes, okay? You can, first of all, you can scale it, and one of the easiest ways to scale it first, okay, is scale by -1. Let's see what that does. If you scale by -1, okay, you will get negative x squared plus 1. That gives us negative x squared minus 1 when you distribute it. That gives us something that looks like this. I'm going to draw it in a dotted fashion. That simply flips it over the x-axis, right? You negate it, the parabola now points downward, or opens up downward, okay, toward the bottom of the page. Okay. We can also translate up or down. Translate up or down, okay, simply by modifying this number. Okay, so instead of x squared plus 1, we can say x squared plus 2, right? X squared plus 2. What happens there? All that does is it moves our y-intercept, okay, to 2. So we're now here. It's the exact same parabola, okay, but shifted 1 unit higher. And it's 1 unit higher because it used to be plus 1, we're now going to plus 2. That's a change of 1 unit, right? So that just shifts all the y values basically to our parabola up by 1. That's why the whole parabola moves up by 1. Likewise, you can say minus 1, right? It'll move down to here. It might move down to here. If you just had an x squared without any constants, it's plus 0, you just get a parabola that goes through the origin, right? Exact same parabola. Now, the last shift we can do, I'll do this one in blue, is left or right, okay? So what that looks like typically is instead of just the x squared plus 1, that was the original, we can say x minus some constant, we'll say x minus 1 squared plus 1. What this minus 1 does, doesn't shift it to the left, okay? That actually shifts it to the right. So x minus 1 actually shifts it to the right by 1. So we'll take that original black parabola, we'll move it over to 1. This point is now here, and we can draw our parabola as such. Okay, so that shifts it to the right. To shift it left, we simply have to say x plus 1, and that would shift it to here, and the parabola would look like this. So it's getting a little messy, but generally plus and minus will just simply change which direction, left or right, up or down. Okay, so there's the 3 basic transformations we should know. Okay, finally here in this slide we'll talk about quadratics. That's a very popular topic you'll see, right? A quadratic equation is typically of this form, of this general form here, right? ax squared plus bx plus c, where a, b, and c are different constants. Now, there's multiple ways to solve for the roots or solve for x, right? To figure out where the graph crosses the x-axis. So if we drew a parabola like this, okay, y equals 0 happens here and here. So the x-axis and the y-axis. And given those, okay, we can solve by factoring the equation, if possible, completing the square, or simply using the quadratic formula here, which is x equals negative b plus or minus, that means there's 2 answers, the square root of b squared minus 4ac all over 2 times a. Now, something very special about this. There's a couple shortcuts that hopefully you won't need to use your calculator for. The thing inside the square root, okay, the stuff in here is called a discriminant. Discriminant. And let me write that out for us here. That's b squared minus 4ac. There's a couple very important things we should know about this discriminant, okay? If b squared minus 4ac is positive, so it's greater than 0, okay, we have 2 real roots. The reason is, if it's greater than 0, you can take the square root of it, and then like we set up here, there's a plus or minus, so it would be negative b plus whatever that square root is, and a negative b minus whatever that square root is. So we'll have 2 different answers, okay? When it equals 0, when b squared minus 4ac equals 0, okay, that's another case, we have 1 real root, and it's a double root, okay? The reason that happens is if you imagine negative b plus or minus the square root of 0, okay, when you add 0 or subtract 0, the square root of 0, you get the same answer. It'll always be, your roots will always be negative b over 2a, right? So that'll be a double root. That's where the parabola just touches the x-axis because there's going to be that double root. Okay, it'll look something like this. I'm kind of drawing it a little sloppy on the side, but it will look just like this. It'll just touch and then come back up. It'll touch it once, but that's a double root, right? Like x squared, for instance. Finally, we have a case where we have b squared minus 4ac is less than 0. It's a negative number, okay? Now, if you recall, when we take a square root of a negative number, we're in this imaginary world, right? It's imaginary numbers, complex numbers. So we'll actually have 2 complex roots. We can just say it's their imaginary roots. Imaginary roots. All right. Great, so let's talk about a couple other things for functions to get us to be a little more solidified and how all these different functions look like. First, we'll talk about lines, or a linear function, right? Okay, if you graph that out, that's very straightforward. It has to look like a line. You go from this point to this point, and boom, there's a line, right? That is simply what a linear function is. You can find the distance by using this distance formula. Okay, so we'll call this point x1, y1, x2, y2 for the coordinates. And you simply plug in this formula to find what is the distance between here and here. Okay. The midpoint can be found in a similar way. You use the x1, y1, x2, y2 coordinates. Plug it into this formula. And finally, of course, the slope of the line. The slope of the line is simply its rise over run. If they give you a graph on the exam and it has the grid lines and you can count the boxes, it could be very convenient too. But otherwise, you simply use this formula. You basically count how many you go up, right? Sorry, how many you go up. I'll do this in green. How many you go up and how many you go over, right? And that's the slope of that line. Now, you might be given 2 points like x1, y1, x2, y2, and they might just say, hey, you have these 2 points. What's the equation of the line? In that case, I strongly recommend you use the point slope form. We just said how to find the slope, okay? So you could plug that into m. That's what m is. That's the slope. And with any 2 points, okay, you can use either 0.1 or 0.2. You just need to be consistent. You can plug in y1 and x1, and you will get the equation of the line, right? The reasoning behind this generally kind of falls under this reasoning. If you have any 2 points on a plane, like this one and this one, there's only one line in this 2D plane that can go through both of those points. There's only one line that does it, and it's that one right there that I just drew, okay? That's pretty unique. So basically any 2 points can define a line. Finally, we have the slope-intercept form, which if you rewrite the point-slope form, you can actually get to the slope-intercept form. But it's a little more refined version where you keep the y by itself on this left side. The slope is here again, and B is known as the y-intercept. Okay. The y-intercept, as represented by this graph we have here, is this point right here. Right? This point. That's exactly where the line crosses the y-axis. The y value where the line crosses the y-axis. That's the y-intercept. Okay. Let's get to a couple more fun, probably more difficult ones. We have a polynomial function. A polynomial function does not have any variables in the denominator. It's usually in this kind of form, like x to the fourth, plus x to the third, and then x to the second. It's just in decreasing degrees, right? 4, 3, 2, 1, and then some sort of constant, maybe plus c, we'll say. Typically, whatever is the highest order, so we have a 4 here, that tells us at most how many solutions, okay, how many zeros this graph will have, or this function has. Again, the zero or a root, however you'd like to call it, is where the function crosses the x-axis, right? Or, in other words, where the function equals 0. So this case here, we've graphed x to the fourth minus 5x squared plus 4, okay? And this graph looks like a nice W, okay? Common shape for a fourth x to the fourth type of function. And you can see very well here, it crosses 1, 2, 3, 4 times. A rational function, on the other hand, does have variables in the denominator. And you see from here, we cannot simplify this any further. That's just how it's left, right? If you recall from our previous slides, we talked about an asymptote and possibly limiting the domain of a function. This is one of those special cases where we see this in action, right? The denominator here cannot be, x minus 1, that's the denominator. It cannot be equal to 0. Otherwise, we'll have x squared plus 3 over 0, and that's undefined. If you look at the plot that's accompanying this on the right side, you actually see that asymptote. I'm going to draw it in a dotted red line here. That's that right there. The graph, you see them kind of going off to the bottom left and the top right. They never touch that asymptote. They never cross, they never touch that asymptote. They get very, very close, very, very close, but it never truly touches that asymptote, okay? So this is what some rational functions may look like. It might not all look like this, but this is just one example. Okay, let's move on to exponential. Y equals 2 to the x. Y equals 2 to the x is our example here. The difference between a polynomial is that the variable x this time is in the exponent. It's in the exponent, okay? So this basically means as x increases by 1 unit, y is doubling, right? And we can kind of confirm that. You can kind of see that going up and shooting up crazy here. So if we had x equals 1, y equals 2. X equals 2 should double it, y equals 4, and so on. So that's an exponential function, okay? Now, it doesn't have to increase. This is because the depends on this base here, right? If we had 0.5 to the x, you might see a function that looks more like this. It might do an exponential decrease like this. Okay, so just keep that in mind. But if you know how to use your calculator, it'll be very quick to know how to visualize these different types of functions. Finally, we have the absolute value, and just to remind ourselves, whatever is inside the brackets here, or these straight bars, the absolute value sign, if it's negative, it gets turned positive, and if it's positive, it stays positive. So this graph we have here as an example, if we didn't have the absolute value bars, would have looked like this. It's just an x squared shifted down 2 units, right? But absolute value takes everything that crosses below here, so everything below here, and flips it up to the positive y region, right? So I'm going to do this in green. This part here is no longer there. It's going to be shifted to here to be positive, right? And that's what you're seeing, this behavior of this weird kind of W shape. All right, in this next part of the review, we're going to talk about logarithms and trigonometric functions. So you should be pretty familiar with logarithms now. I like to think of them as kind of like it's like the opposite of an exponential, right? Opposite of exponents, right? And just to be clear, so we know what this means, right? we say log base a of b equals x, that means a to the x equals b, right? So in other words, if you were left with this here, which we might see a little later on in the sample questions, if you have a to the x equals b and you're trying to solve for x, you can take log base a of both sides, okay? Log base a of both sides, and that gets you x equals log base a of b, right? So that just helps us take down the, remove that base there, that a, and get us to x equals something. In any case, that's just kind of a little tangent. Let's go through these log rules real quick. So this is some sort of product rule where we see if it's base log a times of x, y, this product, it's the same as saying log base a of x plus log base a of y. You can kind of separate them into these sums. Likewise, in this division one here, in this quotient rule, log base a of x over y, when written as a quotient like that, can be written as log base a of x minus log base a of y. So just mind the signs here, okay? So these are kind of the two basic rules. This one here is kind of this exponential rule that can be brought down as a coefficient. Log base a of x to the n power is same as bringing that n down in front as a coefficient and saying n log base a of x, okay? So all we did here was take the n that was here, we remove it and place it in front as a coefficient, okay? This one here is a base change rule, base change, okay? So you notice we start from log base a of b, but you can also write this as log base c of b over log base c of a, okay? Just note that pattern matching. We might use it later. And finally, the log base a of b is also equal to 1 over the log base b of a. So an interesting little reciprocal type rule here. Just to see what a log function looks like, we gave a little example here. This is y equals log base 10 of x, okay? And you see it kind of shooting up very quickly here and then sort of leveling off, okay? Note that it does not touch this y-axis here, okay? That is an asymptote, and we talked about that already, asymptote, okay? Because if you had log base 10 of 0, okay, what does that equal? You're basically asking us to say, well, 10 to what power, maybe we'll call it y here, 10 to what power equals 0, okay? And that can't happen. We can't have that. It's undefined. So moving on to trigonometric over here on the right, we wanted to just make sure we were all familiar with what they look like, but be aware you have your calculator at your disposal on the exam, so it'd be best to graph trig functions if you're not sure how to visualize it, but we think it's a good idea to at least know the three basic ones here. So this one is a sine function, okay? It goes from 1 to -1, okay? 1 to -1. This is y equals sine x. And it's 0 here, this is graphed in radians, right? So at about 3.14 here, that's pi radians, okay? Sine of pi is 0, so that's why we've reached 0 again here. And one full period, that means one whole wave like this, takes 2 pi. If we go over to cosine, it's the same thing. We start from 1, okay, because the cosine of 0 is 1. And then it goes down, and at pi over here, it's at -1. Okay, 180 degrees, cosine of 180 degrees, or cosine of pi radians. And then it comes back up and completes a full period after 2 pi radians, okay? Something to note here is sine is an odd function, okay? Notice over here, everything is, let's say right over here, this is pi over 2. It's at +1, but here at negative pi over 2, it's at -1, okay? So it's kind of this, it's like sort of mirrored on the y-axis but flipped, right? On the other hand, a cosine function here is even. You notice we have symmetry right about this line, right? Everything matches. This point matches to this point matches to this point. This is an even function. And finally, we have the tangent function. Notice how there's multiple asymptotes. We've only included 3 of these graphs here right now, or 3 of the lines, right? But notice from here, it stops, or it starts here, doesn't quite touch this line. We'll figure out what that is in a second. Passes through 0, comes up here, and again reaches an asymptote, okay? Now if we think about the tangent function, okay, we know tangent can also be written as sine over cosine. or we should maybe more accurately say tangent theta equals sine theta over cosine theta. And the asymptotes happen where the denominator becomes 0, right? Because we can't have a 0 denominator. That's undefined. So we know cosine becomes 0 at, or cosine equals 0 at negative pi over 2, etc. So these multiples, right? So we know then that this asymptote here is a pi over 2, this one's negative pi over 2, and then so on and so forth. This next one over here would be pi over 2 plus an entire pi, okay? An entire pi, 2 over 2 pi. So that's 3 pi over 2 would be this one here, and so on. This would be negative 3 pi over 2. And again, it's hard to see in this graph, but if you graphed it on your calculator, it'd be pretty easy to see that. Finally, a couple last things to review for the inverse trig, periodic and piecewise functions. So inverse trig is exactly what it sounds like. It does the opposite of a trig function. This here, this first graph on the top left, the one I've just checked, is the arcsine function. You may also see it written as sine to the negative 1 of x, okay? That should not confuse you. Don't think that's 1 over sine x. That's not what it is. That means it's the inverse sine function. What the inverse sine function does is it gives us back our input, like any other inverse function, right? So for instance, if we say y equals the sine of x, and we say x is, let's say it's pi, okay? X is pi, we know y equals 0. What the arcsine function does is say, okay, we know y equals 0, let's plug it in. Okay, so y equals, I'll write it this way, sine negative 1 of 0. What is y? That gives us what x would have been in the original function, right? It just gives us back what would have been the input of the original function. So in our case, there actually could be multiple answers. It could be pi, it could be really any integer multiple of pi. But in our case, we're restricted to these bounds here we see from negative 1 to 1, which is, if you think about a sine function, the y values only go from negative 1 to 1. So that's why, in this case, our x values go from negative 1 to 1, right? We are doing the inverse function. So we see here, again, you can graph this on your calculator to get a better idea, but this is what the inverse sine function looks like. And I won't go into too much detail really about the other ones here, but this is the arc cosine function, can also be written as y equals cosine with this minus 1 power of x. Note that this over here is the x-axis, right? So it's always positive. Okay, the arcsine function seems to always be positive here, from 0 to just over 3, so that's 3.14. You can guess that's about pi, right? And then finally, the arctan function has an asymptote right about here, okay? And what's special about this is it's actually, if you look at the arcsine, arccosine, they're kind of, in a sense, vertical, right? They're kind of going up and down. The arctan function goes left and right. But once again, you have your calculator at your disposal. So if you ever forget what these look like, just use your calculator to graph it. Should be no problem. A periodic function, okay, a periodic function. The key word here is period, okay? Period basically means something's repeating over and over again. So the example we've chosen here, for instance, this example, is a sinusoidal function, okay? So much like the sine function we had from before. But notice we have a amplitude of 5 here, and then it goes down to negative 5, right? Here's our center line. So this graph is actually y equals 5 sine of x, okay? And that's just one of many different types of periodic functions. There are definitely other ones. We just wanted to show this one here, that it repeats after this one period here. The period is how long it takes to complete one cycle. And that's one cycle right here. Okay, so this is the period. And in our case, it actually equals 2 pi. That's about 6.28 right there. Okay, 2 pi. And then again, it starts here, right? Up and then down, and it's going to keep going. Finally, we have piecewise function. This is basically kind of putting different functions together in kind of simple terms, right? Putting multiple functions together. So if we look in this case, this here that we have, okay, is actually a sine function. This is a sine function. So we typically write it like this. So f of x equals, right? So then we could say here, And you basically prescribe just what the function is at certain x values, right? So from in this left portion here, okay, so that's x is less than 0, basically, less than equal to 0, we can even say. The function is a sine function. So I will say it's sine x, okay, when x is less than or equal to 0. And then it changes. You see, if it were still sine, it would just continue and do something like this, right? However, we see this straight line that goes up, okay, and it looks like it's a slope of 2. It's up 2 over 1, up 2 over 1, right? So it's actually 2x once x is greater than 0. Okay, so this right here is a full definition of this piecewise function we have here. You're basically just putting them together. Now you could have 3 parts, 4 parts. It could be multiple, piecewise function. This is just a 2-part here. But the important thing to take away is that you break them up into their domains, right? It's sine x when this is true. So that's everything on this side of the graph. And it's 2x, the function is 2x, when this is true. And that's everything on the right side of the graph. All right, so let's see if we can start applying some of these algebraic and function concepts to a couple practice questions. So here's the first one. If log base a of 5 is equal to x, and log base a of 7 is equal to y, then log base a of the square root of 1.4 equals. So what's very interesting here is, we're kind of thinking, where did this 1.4 come from, right? We have 7, we have 5, how did this 1.4 get here? And interestingly enough, if we take 7 divided by 5, okay, so 7 divided by 5, we'll actually get 1.4. So maybe there's a way to kind of put this together to see if we can get this log base a square root 1.4. So why don't we try this, okay? So if we had log base a of 7, this whole thing, 7 divided by 5, okay? We'd have log base a of 1.4, right? Now there's that square root, so let's put a 1/2 here. So this is basically what we're trying to get. Let's see if we can kind of decompose that. One of our log rules says that if we have an exponent, which I'll highlight in red right now, this 1/2, we can rewrite, okay, we can rewrite this as this. 1/2, you bring that exponent down, okay, 1/2 log base a of 7 over 5, okay? Now that's really nice. There's another rule we can use, another log rule, okay? So we can rewrite once again, rewrite once again. This log base a of 7 over 5 can be rewritten as log base a of 7 minus log base a of 5, okay? That's another log rule. This is one of those quotient rules. So we already know that log base a is 7. Log base a of 7 is y, and that the log base a of 5 is x, right? So that's just based on what we were given here in the problem. And so just from that, we can very quickly come to the conclusion that this log base a of square root of 1.4 will equal 1/2 times y minus x. Just plug in those in, and that leads us to choice D. All right, in this next problem, f of x is equal to ax plus b, so that's linear. Which of the following makes f of x equal to f inverse of x, right? So we're looking at when would the inverse be equal to the original function, and then it's a couple of these here. So perhaps we can try to set them equal to each other to try to gauge and try to see a different type of form, right? So we have f of x equals ax plus b, right? If we try to do the inverse of that, okay, how do we get that? Okay, what is f inverse of x? So typically what we do is, let's just rewrite this again here as y equals ax plus b. Okay, we're going to flip the variables. Now we have x equals ay plus b and solve for y. Okay, so we'll subtract b from both sides. X minus b equals ay. So y will equal x minus b over a. Okay. So that's the inverse function. This is the inverse function. This is f inverse, okay? We want to know when that will equal the original function. So I'm going to write in red now, and we'll try to reason this out. When would ax plus b equal x minus b over a? Okay, when would these two be equal? So if we go through each choice real quick, might be able to get something. So it says here in the first one, if a equals -1, if a equals -1 and b is equal to any real number. So just looking at that, if a is -1, we'll have -x plus b, and we'll have here, because we're divided by -1, so that's -x, right, plus b. Okay, so those two are equal right now, and if b were any number, these two are equal. So it seems like choice 1 does work, so we confirm that. Let's go to choice 2. So this is choice 1. Okay, let's go to choice 2. Okay, if a equals 1 and b is 0, so a is 1, b is 0 would make us get x plus 0 equals, again, a is 1, b is 0, x minus 0. That also works, right? So that confirms choice 2. And then the last one, I'm going to squeeze it down here, choice 3 here, a any real number, b equals 0. Okay, so we'll have here ax, where a we don't know what it is yet, ax plus 0 equals, and that's x over a, and b is 0 here, so that's plus 0. Okay, so that you can tell is not exactly the same. We reject choice 3, so we are left with answer choice D, which is only 1 and 2, because we reject that third one. Okay, so in this next question, we're being asked if f of x is equal to the absolute value of x plus this bracket notation, x, we'll talk about that in a second, the value of f of -2.5 plus f of 1.5 is. So what the question is asking is very simple. We really just have to know what these two mean, right? So this is absolute value. You just make whatever value is in it positive if it's negative, and if it's already positive, you keep it as that same number. This here finds the greatest integer, okay, so no decimals, greatest integer that is less than or equal to x, okay? So here's how I propose doing it, just so we don't get confused. Why don't we do it separately? Let's do this f of 2.5 first, or -2.5 first on this side, f of 1.5 here, and then we can just add them together at the end, right? Because there's a addition sign here. So let's just do them separately and see where that gets us. So for the first one, we have f, right, we have f of -2.5 is equal to the absolute value of -2.5, okay? That should be a straight line, plus the greatest integer that's less than or equal to -2.5. That evaluates to positive 2.5, okay, minus 3, or plus -3. I'm just kind of combining those two signs together. And the reason for that is -3 is the greatest integer that is less than or equal to x. Remember, our x is -2.5. So to go less than, you have to go more negative. So that is -3. And then when you combine that together, this fully evaluates to, okay, this fully evaluates to -0.5. Let's do the right side here. F of 1.5, okay? So that will equal the absolute value of 1.5 plus the greatest integer less than or equal to 1.5, right? So this evaluates to 1.5, it's already positive, plus, and now we're going less than or equal to, we can actually round down here, right? So it's actually going to be plus 1. That gives us 2.5. Okay, and the problem overall is asking us to combine these two, so we just add them up, right? 2.5 plus -0.5 will equal 2, right? So D here is our answer. Right, in this next question, a company offers you the use of its computer for a fee. Plan A costs $6 to join, then $9 per hour to use the computer. Plan B costs $25 to join, and then $2.25 per hour to use the computer. After how many minutes of use would the cost of Plan A be the same as the cost of Plan B? Okay, so let's just be clear here. They're giving us an hourly rate, and eventually we'll have to convert to minutes. So we'll just keep that in mind. Okay. Let's write each of these as some sort of function. We'll use some algebra to generate this function, just to model the situation we have here, right? So plan A, I'll let A be how much that plan A will be, okay? Will equal $6 upfront plus the 9 per hour, so 9T, to use that computer, okay? So that will model that situation. Plan B is on similar lines here. B will equal $25, that much higher upfront cost, but only $2.25 per hour, okay? So what the question's basically asking us, okay, if we can boil it down, is when does A equal to B? That's what it's asking us, right? When are the two costs equal? We have equations for them, so why don't we write out this equality? 6 plus 9t equals 25 plus 2.25t, okay? We'll subtract 2.25t from both sides and subtract 6 from both sides. That way we can group together like terms. We'll be left with 6.75t equals 19. Solve for t, okay? Solve t, and that equals 2.814 and so on hours, okay? That is in hours. So now we have the answer. We know it'll take 2.814 hours. It's asking us to convert it to minutes, okay? It doesn't say it explicitly to convert, but these answer choices, as we see, are all in minutes. So we know there's 60 minutes to an hour, 60 minutes to an hour, and we're just trying to convert this 2.814 hours, okay? So really we're just multiplying by 60, right? And when we multiply by 60, we get approximately 168.8 repeating minutes, okay? And the closest answer that gets us there is choice C. Right, in this next problem, if f of x is equal to the square root of the quantity 2x plus 3, and g of x is equal to x squared plus 1, then what is f of g of 2? Immediately, we should recognize right here, this is a composite function. Composite, or a compound, you might hear it as compound as well. Okay, it's a composite or compound function. And all we have to do, we just take it step by step, okay? Let's look inside the parentheses first, g of 2. G of 2. We're going to use that output and put that in f. But let's do g first. Let's take it one step at a time. G of 2, using this, right, as g, will equal 2 squared, just plugging in for x, plugging in 2 for x, plus 1. That's 4 plus 1 is 5. Now, it asks us to do f of g of 2. We now have just found g of 2 is 5, right? So we're now looking for what is f of 5. Okay, we just follow the steps one at a time. So that will equal the square root, I'm now using this formula here, of 2 times 5 plus 3. Okay, 2 times 5 is 10, plus 3 is 13. So we're really looking at the square root of 13. Now, we'll just have to use our calculator here to get the decimal answer. Okay, and if we do that, we'll get approximately 3.605 and so. And that will round to 3.61, which gives us answer choice C. All right. A new machine can produce X widgets in Y minutes, while an older one produces U widgets in W hours. If the two machines can work together, how many widgets can they produce in T hours? Let's just note there's minutes here, there's hours, so we're going to have some sort of conversion from that minutes to hours, right? Because the answer we eventually want is in hours. Okay, so let's break it down. Let's look at the new machine first. Okay, the new machine can do it at this certain rate. Okay, X widgets in Y minutes. Let's quickly change this to hours because this is in minutes right now, right? So let's multiply by 60 minutes in an hour. That'll give us 60x over y. Okay. In doing so, we know how many widgets we can make in an hour. Okay, so that's the units here are now widgets, widget per hour, which is good. This is exactly what we want, this rate right here. Let's do the old one real quick. So this one's pretty easy. It's pretty, it's just given to us. It says U widgets, okay, U widgets per W hours, okay? So it's just this here. So then we have these two rates, basically. We basically have these two rates. They're now going to be working together, and we need to know that combined rate, right? So let's say they're working for T hours, as we're given here. They're working for T hours. So the new one would produce whatever its rate is, so rate new times T. That's how many widgets, okay, widgets made by the new machine. We need to add that to the rate of the old machine times the same T. Okay, that will give us the widgets made by the old machine, and that will give us the total, which is what we're looking for, as the total widgets they could produce in those T hours, right? Now we just said what the rate is. We can just plug in now. This is the rate for new. This is the rate for the old, right? So when we plug that in, we notice we can pull a T out. Everyone has a T for the T hour, so we can just pull that out. And we have the new rate 60x over y, and we can add that to the old rate, which is u over w, okay? And just do a little pattern matching, and we can see it is not choice A, but it sure looks like choice B. So if n is an integer, what is the remainder when 3x to the 2n plus 3 minus 4x to the 2n plus 2 plus 5x to the 2n plus 1 minus 8 is divided by x plus 1? So you could try to do long division here, but I would not recommend it. It will take a very long time. What's better to know here is the remainder theorem. Okay, and the remainder theorem basically says if we're dividing by this x plus 1, we can find the remainder simply by plugging in, just plug in -1. Okay, just plug in -1. And the reason is that's what would make this 0 on the bottom, okay? It's almost kind of like trying to find a root, right? If you plug that in and it gets you 0, then the remainder is 0. So in the same way, we could figure out what the remainder is just by plugging in that -1. So why don't we just do that? So we have 3 times -1 to the 2n plus 3, okay, minus 4 times -1 to the 2n plus 2, plus 5 times -1 to the 2n plus 1, all subtracted by 8. Okay, so this is how we're finding the remainder. So now we have 3 times, we got to do PEMDAS, so we got to make sure to do all this exponent stuff on the right here first. We have -1 to the 2n times -1 to the third. Okay, I'm just breaking it up using exponential rules, right? So we could just do this. Minus 4 times -1 to the 2n times -1 to the second power, plus 5 times -1 to the 2n times -1 to the first power minus 8. Now, -1 to the 2n. N can be any integer, right? So regardless if we put an even number or an odd number in there, because we're multiplying it by 2, it's going to be an even power. And -1 raised to any even power, let's say -1 to the fourth or -1 to the second, will always just become +1, okay? So being able to see that, we can change this to a 1, we can change this to a 1, and change this to a 1. In fact, we can even change this to a 1, okay? What we can't change to a 1 is this, because it's an odd power, and this one's an odd power. Because they're odd, okay, -1 to the third actually becomes -1, and -1 to the first power also becomes -1. So now we're left with -3, okay, -4, -5, -8. Okay, that's what's remaining of this. And if we combine these all together, okay, -3 minus 4 is -7, -5 is -12, -8 is -20. Okay, and with that, we know our remainder is choice A, -20. Okay, If f of x is equal to ax squared plus bx plus c, and f of 1 equals 3, f of negative 1 equals 3, then a plus c equals, okay? We know we're working with a quadratic here, okay? So just to get an idea what this might look like, they said that f of 1 is 3 and f of negative 1 is 3, right? So it might be some sort of something like this, right? It could even point downward, we're not really sure, okay? But in any case, it looks like it's going to be symmetric about this y-axis here, this y-axis. So what does a plus c equal? So we're given this info, and we should probably use it. We basically know 2 points. We know 1 maps to 3, negative 1 also maps to 3, as we sort of tried to sketch out in this diagram on the left. So why don't we plug that in? So we have f of 1. Okay, so we now have a times 1 squared plus b times 1 plus c. And we have f of negative 1 equals a times negative 1 squared plus b times negative 1 plus c. And now it's asking us, right, what is a plus c? Okay. So this is pretty trivial at this point. We know this is equal to 3. We know that this is equal to 3, right? So they're basically equal to each other right now. So let's rewrite here. So we have a squared, this is a plus b plus c equals 3. And now we have negative a, that's positive a, right? Negative 1 squared minus b plus c equals also 3, okay? And it's asking us what is a plus c. So if we combine these two equations right now, just add this, we get 2a, this goes away, plus 2c equals 6, okay? And if we divide everything by 2, all sides by 2, we get a plus c, that's exactly what we're looking for, equals 6 divided by 2, which equals 3. And that leaves us with choice D. All right, in this next problem, we're very simply asked to perform a limit, okay? And that basically means what happens to this rational function we see here when x approaches infinity, as x keeps growing, okay? One of the easiest ways to do these, instead of actually working it out, is to use your calculator. All right, and when you use your calculator and you start zooming out, you'll get a graph that looks something like this. It's not going to be very accurately drawn, but it kind of looks like this. Draw it in blue here. So it's kind of got, just copying from my own calculator here, it's kind of got this thing that goes out this way, okay? It's got this little squiggle that comes in here, okay? And then it's got this part that goes like that, okay? So if you keep zooming out on your calculator, you will find that as x goes to infinity, right? As x goes to infinity here, this will keep growing without bound. The meaning of that, translated to relevant terms in this problem, that's the limit as x goes to infinity. If it's growing without bound, that means the function is also tending to go to infinity. So that's choice E, okay? Another way you can actually look at this is to just look at the highest exponents here, because those will be the ones determining the behavior of the function. We don't have to look at the x squared and these constants here. So we're really just looking at 3x cubed over 4x squared, right? Just looking at that. And when we look at that, we can again kind of get rid of the coefficients. It's really the x's that matter here. We have an x cubed on top, x squared on the bottom. And if you divide that, you just get an x, right? That means as x goes to infinity, okay, the function kind of behaves like x, right, as a linear function. It'll just keep going to infinity in that straight line, okay? So that's another way to kind of look at it. But again, the calculator is probably your best friend here, so I would definitely recommend that. The domain of f of x equals log base 10 of sine x contains which of the following intervals? Okay, we should probably think about first what log can be, okay? So I don't remember from the top of my memory, let's say, what a log function looks like, that is quite okay because you can plug that in to your calculator. So if we plug that in, okay, we do the log base 10 of x, we'll call it x for now, okay. That function looks something like this, okay. It's here, and then it goes kind of like this, right? Now, the very, very important thing to note here is that this log function, and maybe I should write it, this is y equals log base 10 of x in general, just random x, right? It approaches this asymptote here, okay, at x equals 0, okay? Does not touch. It approaches that y-axis, but it doesn't touch it, right? The reason is if you do log base 10 of 0, right, that is actually undefined. That's undefined. Because that's basically asking us, right, what is, 10 to the what power equals 0? And there's no such thing, right? So that's undefined. So that tells us that whatever is in this parentheses, we've been calling this whole thing x right now, but we'll have to make a distinction that there's a sign x here. That cannot be 0. Okay, sign x cannot be 0, but it can be anything else. So anything that's saying it can be 0 can very quickly be eliminated because sine of 0 equals 0, right? Very important to note. Sine of 0 is equal to 0. We can draw that, sine of 0 would be over here, 0 degrees, okay? In which case the cosine of 0 is actually 1. If we drew a unit circle or a unit triangle, however you guys usually draw it. In any case, it's also 0 here at pi, okay? That's where sine is 0. So any answers that have sine of 0 is 0 or sine of pi is 0, right? Those can be eliminated. So there's a pi here, there's a 0 here, and it's saying less than equal to. We can't have that, not a. How about here? That's saying from negative pi over 2, that's down over here, to pi over 2, that's over here. That passes through, right, the 0 degrees here, or 0 radians. That can't be the answer. However, I'm starting to like this answer here at C. 0 is less than x is less than pi, right? So that is this entire semicircle up here, but without the two endpoints, okay? That seems like a good answer so far, so I'll keep a check on it, just double check the last two. D is similar to B, that 0 is included in that range, so we don't like it. And the final one for E, we're seeing pi over 2, that's up here. This is pi over 2, okay, 90 degrees. And 3 pi over 2 is down here, and that passes through pi, which we said is not allowed as well. So not E, confident choice C. All right, so if x, there's a little typo here, if f of x is equal to x squared minus 4, for what real number values of x will f of x equals 0? So very quickly we recognize once again this here, that's another composite or compound function, right? Composite or compound, where you're using the output of one to put it into the input of another function. Interestingly enough, we're only given one function. It's just f, right? So this is also known as a recursive function. It's when a function uses itself again, okay? So it's asking us, when will this equal 0? So we're looking at f of x, okay? Let's plug in, this is f of x. So we're looking at what is f of x squared minus 4. We now have to plug in, so this is kind of where it's sort of like an inception, right? We're now plugging in this as x. We got to plug that back in now to that x, okay? So we're looking at x squared minus 4, that is x now, squared minus 4, okay? So that's that recursion. Let's try to solve and see what we can get. So they want this to equal 0. Let's place a 0 here. Add 4 to both sides. 4 equals x squared minus 4, okay? And that's squared. If we square root both sides, square root, okay? For the left-hand side, the square root of 4 could be positive or negative 2, and that will equal x squared minus 4. Okay, so it's pretty simple here. There's two ways to go, two solutions. We'll do the plus 2 first. So we have plus 2, right, equals x squared minus 4. Very quickly solve for x here just by adding 4 to both sides. That's 6. Okay, 6 equals x squared. In the second one, we have minus 2 equals x squared minus 4. If we add 4 to both sides, we get 2 equals x squared. Just by square rooting, we can find the answer to this question. So the square root, that we'll do the first one, of 6 is about 2.4, or 2.449. And the square root of 2, again, just putting these in my calculator, is 1.4, okay, 1.414. Now, when we look at this, okay, we knew we had a x to the 4th happening here, because there's an x squared here right now, and that's squared. So we know there's probably, or there could be, up to 4 different answers to this. Now, when we square rooted here, when we did the square root, just remember, these can also be positive or negative, right? Because if we square 1.414, we'll get 2. If we square negative 1.414, the negatives go away and we still get 2. So the answers are really these positive negatives, 4 answers, and that is answer choice D. Okay, if f of x is equal to the cube root of x and g of x is x cubed plus 8, find f. This is an f, this is like FOG notation, right, of 3. That, again, we've seen many times already. This is also a composite function or a compound function. Okay. Basically, we do g of 3 first and then perform f on that. So we've seen this in this sort of form, f of g of 3. This is what we're doing, okay? Just to not be confused. So let's do g of 3 first, and it's very simple plug-in type of problem here. So g of 3 will equal 3 cubed, just following this right now, 3 cubed plus 8, okay? 3 cubed is 27. 27 plus 8 is 35. Okay. Now we have to plug that into f of x. So f of 35, right? We're just plugging it in here now as the solution from g of 3. That's plugging into here. That should equal the cube root of 35. Okay. Now you can simply put that on your calculator. If you don't know how to use the cube root function on your calculator or something, you can also say 35 to the 1/3 power, right? Just using exponents here. It works the same way. That should say 3. There we go. 1/3, right? And when you solve that out, you will get approximately 3.27. And just looking at the answer choices, the closest one here is answer choice A, 3.3. Okay. If f of x is equal to 2x plus 1, then f to the negative 1, so that's the inverse, right, inverse function, of 7 equals, okay, so this is a pretty fast way to do this. Remember what an inverse function does, right? If we have a function f, it'll take x and spit out y. The inverse function will tell us if we give it y, we give it the answer we want, it will give us x. So basically, this 7 here is the output of the original function. So it's asking us at what x, okay, will f of, maybe I should write that here, at what x will this f of x equal 7, right? So we could just say 7 equals 2 to the x plus 1, okay? And then we subtract, so we can say 6 equals 2 to the x, okay? At this point, you could probably brute force it on your calculator. Okay, and you basically just plugging in all of these values as x. There's only 5 values, it doesn't take that long. If you want to solve it more thoroughly, of course, or just in a more algebraic fashion first, we can always take the log base 2 of both sides, okay? And if you solve that, and I'm going to try it right now as well, we'll just make sure we're getting the same answer. The log base 2 of 6 is 2.585, which is approximately choice B. And if you plug that in as well, when we were at this stage, you'd get the same answer. So, pretty short problem. All right, in this next question, they say p of x, this function here, equals x cubed, okay, equals x cubed plus 18x minus 30, has a 0 in which of these intervals? Okay, now, the fastest way, I hope your mind kind of went straight to this as well, let's put that in the calculator, right? You have that graphing calculator, and let's use it to our benefit at this point. So when we put that in a calculator, we get a graph that looks something like this. Okay, yeah, it looks something like this. Okay, and what's important to us is we're looking for the zeros. There could be up to 3. There are some cubic functions that might look something like this. 1, 2, 3, right? Crosses it 3 times. But in our case, it looks like when we kind of zoom in to the relevant area here, it looks like there's only one place that it crosses the axis, right? And when I zoom in, at least, when I zoom in, okay, it is indeed just at one place. I'll kind of draw what I'm seeing right now. So it's kind of like this now. We're zooming in here, okay? And all we have to figure out now is where is that 0? So your calculator might have functionality for that to find where the 0 is, and you can simply see which one of these ranges it falls in, or you might just have to kind of count the little tick marks and find which interval that is. I'm using my calculator's 0 function in order to find it on my TI Inspire CX CAS, okay? And I'm finding basically that the point that intersects the axis is 1.4848, etc., right? Now we simply have to look here in the answer choices and very quickly find that that falls within the interval that answer choice C provides. So that should be answer choice C. All right, and this question here is the last one of our algebra questions, and then we'll move on to geometry. What is the domain of the function f of x is equal to the log the square root of 2x squared minus 15? Again, easiest way to visualize it, why don't we put it in our calculator first, okay? And that might, just by inspection, we can figure out what the domain is. So that's a log, implicitly base 10, it doesn't tell us, so at that point we can just assume it's a base 10 log, okay? Of the square root of 2x squared, okay, 2x squared minus 15. The graph will look something like this, okay? So we'll draw a graph. Okay, and it looks very, very strange, looks something like this. Kind of just stops abruptly here, and then kind of comes up, crosses the axis, and then kind of levels out, and then kind of this mirror image here. Okay, so it's really interesting type of graph, and we know it would be interesting. We knew it was going to be interesting because a log function is pretty interesting on its own, and then we have a square root where you can't have a negative inside, right? So very interesting function. And when I'm looking at my my screen, I can tell this is at approximately 2.7, and this is at approximately negative 2.7. They're pretty much mirror images of each other, okay? So really quickly, just looking at the answer choices, x is less than 2.7, x is greater than 2.7, seems to fit the bill, right? Because the function is defined for anything, I'm drawing in red now, anything from here and less, and anything from here and greater, okay? So not much to do here, you just plug it in your calculator and you can very quickly see where the domain is, and that's answer choice C.
All right, let's review geometry and measurement. All right, on the topic of angles, we have a few types. We have vertical angles. And these are angles that, when we have two intersecting lines, are across from one another. These angles that are across from one another are equal. So we have angle A equal to angle A. They're across from one another. Same thing with angle B. They're across from one another. They're equal. Next up, we have corresponding angles. And now when we have corresponding angles, that's when we have two parallel lines, like in the diagram shown, that are cut by a transversal, which is what this line is called. Now, when we do that, corresponding angles are equal. So that's this angle, which is an angle formed by the transversal and line L, and this is the corresponding angle, right? Where that transversal and line M. So these angles correspond to one another, and the same apply to all the other angles that are formed by this transversal and these two parallel lines. Now, next up, we have supplementary angles. And that's when, let's give an example here, when angles add up to 180 degrees. Now, let's take angle B and A here. Angle B plus angle A add up to 180. In the same manner, we have complementary angles. And that's when angles add up to 90 degrees. Moving on to triangles. When we're looking at the sides of the triangle, we have equilateral, isosceles, and scalene. Equilateral means you have all sides equal. Isosceles mean that you have two sides are equal. And scalene means no sides are equal. And we can organize it by angle as well. Acute triangle where all three angles are less than 90. A right triangle where one angle is 90 degrees. And an obtuse triangle where one angle is greater than 90 degrees. We're going to cover right triangle after we do this general topic of triangles. For triangles, some general properties that are good to know. Area is equal to 1/2 base times height. The interior angles sum to 180 degrees. And finally, we have this triangle inequality theorem. Let's do a arbitrary triangle here. A, B, C, where the lengths of two sides, if you sum them together, A plus B, that sum has to be greater than the third side, and this applies to B plus C as well, is greater than A. C plus A is greater than B. And by extension, there's also a lower limit to each one of these sides, which is the difference of the two sides. All right, moving on to right triangles. In right triangles, we have the basic Pythagorean theorem, which is a squared plus b squared equals c squared. In addition to that, you have special right triangles. Now, special right triangles are 30, 60, 90 triangles, which you see here, where the side opposite from the 30 degrees is x, the hypotenuse is 2x, and the side opposite from 60 degrees is x radical 3. In the same way, we have another special right triangle, which is the 45, 45, 90 triangle. So in that case, both legs of the triangle are x, and the hypotenuse is x radical 2. I'd like to quickly go back to the Pythagorean theorem. You also have this thing called Pythagorean triples that you should know. A few good ones to know are 3, 4, 5, and you also have 5, 12, 13 right triangles. So just those are pretty common numbers that some tests use. So that's 3, 4, 5, and 5, 12, 13. So for quadrilaterals, we have rectangles and parallelograms. Rectangles have an area of length times width, and we know that if it's a square, length equals width, so the area of a square is just the side length squared. For parallelograms and rhombi, the area is equal to length times height. Now, we just have to note that when you have a rhombus, all sides are equal in length. For trapezoids, the area equals base 1 plus base 2 over 2 times the height. And the sum of the interior angles sum to 360 degrees. And we're going to cover that here with interior angles. Now the interior angles of a convex polygon is defined as the number of sides minus 2 times 180. And we can verify this with our triangle where we have 3 sides. 3 minus 2 is 1 times 180, and we know that the interior angles of a triangle is in fact 180. So let's move on to circles. Now circles have a few properties. Area equals pi r squared. Circumference equals 2 pi r. And we should note that 2r is the diameter. So we can also say that the circumference is pi d. The full circle covers 360 degrees, and the standard equation for a circle is x minus h squared plus y minus k squared equals r squared, with h and k being the coordinates of that center point and r being the radius. Another few parts of the circle that we have to note is arc. Now this arc is defined as a fraction of the angle that it makes over 360 times the circumference. Now why is that? We're taking the portion, the fraction of the circle, and we're multiplying that by the total length of the circumference. So we can do this, we can extend that same thing to the area of the sector, the area of this slice of the pie, right? Where we just take the fraction it covers and multiply it by the total area. A few more notes that I like to cover. A tangent line to a circle is parallel to the radius. And we also have inscribe angles. This one's slightly more in depth, but you have a angle inside a circle, and these are called chords. And a cool special property is that the angle this makes, no matter where it is inside this circle, is actually equal to half this angle that's created when we connect these two to the center point. All right, moving on. All right, now we have an ellipse. Ellipses have the equation x minus h squared over a squared plus y minus k squared over b squared equals 1. Now ellipses have two foci. If these foci are further apart, the ellipse is further squished. And if they're close together, so close in fact they're on top of each other, that means the eccentricity is 1, and that is a circle. All right, so h and k here are that's our center point, and a and b represent our semi, minor, and major axis, respectively. Our major axis is our longest axis, which is represented by 2a. So a is just this length here, and same thing on the other side, b is this length here. I'd like to note that if this were oriented vertically, this ellipse, that our a and b values would be switched because the major axis is on the parallel to the y-axis. All right, moving on to hyperbolas. Hyperbolas have the form x squared over a squared minus y squared over b squared. Now you can see the difference between the ellipse and the hyperbola in their signs between their x and y's. Hyperbolas have that minus sign. One thing to note about hyperbolas is you have two asymptotes and you have two foci on either side. Now to get our a and b values, what we'd have to do is draw a line from this point on the hyperbola to the asymptote, and this creates like a rectangle or a box. And then this would be our a value, and this would be our b value. Now there's also one thing called the latus rectum that I have to just cover quickly. Now what that is the line, let me color it in green, the line that connects the foci to the hyperbola. So the length of this is defined as 2b squared over a. Alrighty, moving on to polar coordinates. Polar coordinates, like Cartesian coordinates, present a point in space. So let's say we have these axes over here, this point is here. R would be the length from the center, from the origin, and theta is the angle it makes from the x-axis. I'd like to note here how to convert between radians and degrees. So if we were to multiply radians by 180 over pi, that's how we get our degrees. We can just flip this around, and from degrees, if we multiply by pi over 180, that gives us our radians. So on the topic of volume, you have a few of these on your reference sheet, but I wouldn't really rely on them because there's so little of them. They give you the volume of a sphere, cone, and pyramid, and also the surface area of a sphere. But I advise to just memorize them, right? The volume of a cone is 1/3 pi r squared h. The surface area, I don't think you really have to remember, but it's 1/2 cl, with c as a circumference and l as a slant height. The volume of a sphere is 4/3 pi r cubed. The surface area of a sphere is 4 pi r squared, and the volume of a pyramid is 1/3 base times height, with base being the area of the base. So if they give you length times width for that, that's what you should do. All right, so moving on to rectangular prisms. You have a volume of length times width times height, and you have an area of 2 times the sum of length times width plus width times height plus length times height. And finally, for a right cylinder, you have a volume of pi r squared h with an area, a surface area of 2 pi r times r plus h. This essentially just breaks down the cylinder into 2 circles and a rectangle. All right, moving on to trig. For trig, the most important mnemonic to use is SOHCAHTOA. This tells us that the sine of an angle is equal to opposite over hypotenuse. The cosine of an angle is equal to adjacent over hypotenuse. The tangent of an angle is equal to opposite over adjacent. And that's where this you can just refer to this right triangle over here. Now we also have a special property in trig where we have sine squared theta plus cosine squared theta equals 1. In addition to that, we also have the law of sines, where for any triangle, we'll call this side A, this side B, and this side C, and we'll call the angles opposite to each of them, the capital letter of their side names. So we know that in the law of sines that A over sine of angle A equals B over sine of angle B equals C over the sine of angle C. Another rule that is less important in this exam, but is still good to know, is the law of cosines. So again, with any triangle, we have, so let's refer to this diagram that I drew up here, c squared, the length of c squared, equals a squared plus b squared minus 2 times the length of a times the length of b times cosine of angle c. All right, adding to trigonometry, we have our double angle formulas for trig. We have sine squared theta equals 2 sine theta cosine theta. Cosine 2 theta equals cosine squared theta minus sine squared theta. Cosine 2 theta equals 2 cosine squared theta minus 1. And cosine 2 theta equals 1 minus 2 sine squared theta. And finally, tangent 2 theta equals 2 tangent theta over 1 minus tangent squared theta. In 3D coordinates, I'd like to note how the distance equation applies here. We know that for 2D, the distance equals x minus x0 squared plus y minus y0 squared, and we square root that to get our distance. In 3D and further dimensions, it's the same thing. We have x minus x0 squared plus y minus y0 squared, but then with 3D, we have that extra variable z minus z0 squared. So that would be the distance equation in 3D. the circumference of the circle x squared plus y squared minus 10y minus 36 equals 0 is, well, this doesn't really look like our typical circle equation, right? We're used to seeing circles in center form, which looks like this, with h and k being the center and r being the radius. And if we were to get this is in standard form, if we were to get it into this form, we'd be able to get r, and we can just do 2 pi r to get the circumference that we need. So let's see. Let's write this out. X squared plus y squared minus 10y, and I'm going to put 36 over to the other side. All right, we're getting closer. But now what we have to do is do something called completing the square. We have x squared plus, I'm going to put this in parentheses. We're going to add a number to this side, and to balance it out, we're also going to add a number to this side. And by adding the number here, we can somehow split this polynomial up into its components, right? And that's our goal, to try to get into y minus k squared. So the rule of thumb here is to do b over 2a squared to get this value. And in this case, this would be a is 1, so we just remove that. And we get negative 10 over 2 squared. This is equivalent to 5 squared, or negative 5 squared. But squaring the negative just removes it, so we have 25 in this case. And so our term here is 25 and 25. Let me write this out again. X squared plus y squared minus 10y plus 25 equals 36 plus 25 is 61. And now that we have this polynomial, we can separate it out into y minus 5 squared. So clearly we have a circle here. We converted it into our center form, whose center is at 0, 5, and whose radius squared, this is radius squared, right? So its radius is radical 61. All right, so now that we have a radius, we can just do 2 pi r. Doing this, we get 49.07. And that's most closest to answer choice B. 20 asks us if the vertices of the triangle are U0, V8, and 0, 0, then the area of the triangle is, let's visualize this. Draw a graph. We have one vertex at 0, 0. We have one at U0. And we have another one at V8. So that could be anywhere as long as this is 8. So it could be anywhere here. I'm just going to put it here for now. So we know that the area of a triangle is 1/2 base times height. All right, and now that we've drawn this out, we know that our base is down here, right? And we're just trying to find height. But wait, we have our base, right? So that's u in this case. So our base is u, 1/2 u times height. Our height is just 8. We have it too. Therefore, just multiplying this out, we have 4u. And that means our answer is answer choice A. In 21, we have a cylinder whose base radius is 3, is inscribed in a sphere of radius 5. What is the difference between the volume of the sphere and the volume of the cylinder? Let's draw this out. We have our sphere. Whose radius is 5, remember that. And we have our cylinder inside. With radius 3. So you know that this length over here, let me just draw center of this circle of the base to that edge is 3. All right, so let's quickly calculate our volume of the sphere. Since we already have all the information for that, we know that the volume of the sphere is 4/3 pi r cubed. That means our V sphere, calculating that out, is 523.5987. All we have to do is find the volume of our cylinder. We know that that formula is pi r squared h. So it looks like we're missing the h. We have our r, right? We have our 3, but we're missing our h. So how do we find that? Well, we can try to draw a line from that center of everything and meet the radius of our cylinder base there, as well as meeting the surface of our sphere. Well, that in fact is the radius of our sphere, right? Which is 5 units. Well, in that case, we can even go as far to say that we can drop this down, we can draw a line here, and this creates a right triangle. And looking at we have a leg of 3, we have a hypotenuse of 5, that means it's a 3, 4, 5 right triangle. Meaning we don't even have to do the Pythagorean theorem if we know the special right triangle. If you don't know it, you can easily use Pythagorean theorem and calculate it out yourself. And now we have half the height of our cylinder, right? So by just doubling 4, we get 8. So our height is 8. So V cell equals, looks like it's going to be 226.1946. And we can subtract V sphere minus V cell to get a value of 297.404. And it looks like our answer choice is going to be B. Alrighty, so for 22, we have a plane whose equation is 5x plus 6y plus 10z equals 30. Forms a pyramid in the first octant with the coordinate planes. Its volume is, so let's draw our first octant. Let's have this as our positive y-axis. Let's have this as our positive x-axis. And this looks like our xy graph, right? And let's add our third dimension, c. So let's try to find what this looks like. We know that the plane has to be in this, that intersects all these 3 planes. So let's see where at, okay? So let's start off with our xy axis, just for simplicity. So if we were to find where this triangle, where this plane would intersect the xy axis, we'd have to set z equals 0. So we're stuck on that we're stuck on that plane, right? So let's set z equals 0. 5x plus 6y plus 0 equals 30. Let's try to find what that looks like. It's going to look like a line, right? So let's keep 6y on this side equals minus 5x plus 30. Divide 6 on both sides, and we get y equals negative 5/6x plus 5. Therefore, we see our y-intercept at 5. Let's draw that in. It's at 5. And we have our x-intercept at where y equals 0, right? 0 equals negative 5/6x plus 5. Subtract 5 on both sides. Cancel out the 0, the negative sign, sorry. Multiply both sides by 6/5, right? And then 5's cancel out, so we get 6 equals x. Therefore, we have another point here at x equals 6. So therefore, we have our first line at which this plane intersects this coordinate plane. All right. So we can do the same exact thing to find this. All we would need is to find the z-intercept to find out where this this other line lies, right? These other two lines lie. So let's go with our xz plane in this case. So that means y is set to 0. So we have 5x plus 10z equals 30. Let's just solve for x since it's easier. 5x equals negative 10z plus 30. X equals negative 5z, sorry, negative 2z plus 6. So in this case, we can see that our x-intercept is still indeed at 6, but we need to find the z-intercept. So set x equals 0 equals negative 2z plus 6. And working this out, we get a z equals 3. Therefore, we have a 3 right here. And we can, since we have all the intercepts, we can just connect all these. And the plane that this makes is our plane here. So how do we find the volume of a pyramid? Well, that's just 1/3 base times height, right? In this case, let's make our base, I'll color it in purple, let's make our base this side over here. So with that being our base, it's just the area of a triangle, right? So we know that, let's color it, let's have a green color. This base would have an area of 1/2 base times height. In this case, base would be 3 and height would be 6, so just 1/2 times 3 times 6. And in that case, we can just plug this area into our base. So 1/3 times 1/2 times 3 times 6 times our height, which is just this 5 over here, right? And that gives us a value of, we can cancel out the 3's, 6 over 2 is 3, so all this turns out to 3 times 5 equals 15. Therefore, our answer is 15. In triangle ABC, if sine A equals 1/3 and sine B equals 1/4, sine C equals, well, we can get the angle measurements of A and B by using inverse sines, right? So it stands to reason that we can subtract those values from 180 and get our angle of C and just take the sine of that. So let's do this. We know that assuming your calculator is currently in degrees, if it's in radians, if you're in radians, this 180 would be pi, right? Rather than 180. So, and subtract those two angle values from 180. So we have the inverse sine of 1/3 and the inverse sine of 1/4. This corresponds again to A, and this corresponds to B. And this gives us our angle measurement for angle C. And then we can take this entire value that we get, the angle, and just take the sine of that. And again, if you were to use radians, replace that 180 with a pi. But in both cases, you get an answer of 0.558. And it looks like the answer closest to that is answer choice C. In 24, we have the length of the major axis of the ellipse, 3x squared plus 2y squared minus 6x plus 8y minus 1 equals 0 is, well, we know our equation for our center form for our ellipse is x minus h squared over a squared plus y minus k squared over b squared equals 1, with h and k being our center values, and a being our semi-major axis, b being our semi-minor axis. So let's take a closer look. So how do we get from here to here? That's the question. Well, it looks like we're going to have to do completing the square. Let's group up our x values and our y values and put the 1 on the other side. Let's factor out our a coefficients so that so that we can do a completing the square, because a has to be 1, our leading coefficient. So 3x squared minus 2x plus something, and we're going to add that to our factor out the 2, y squared plus 4y plus something. And we have to reflect that on the other side, 1 plus something plus something. All right, so let's complete the square. So what does this value have to be? Well, let me do it in a different color. Well, the formula is b over 2a with a equal to 1. This doesn't matter, so just b over 2 squared. So for our x values, b over 2 squared is negative 2 over 2 squared, which is negative 1 squared, which is positive 1. For our y polynomial, we have our b value equal to 4. 4 over 2 is 2. Squared is 4. So let's write this out. What does it look like? We can simplify it into its x minus 1 squared. And then we can do the same thing on this side. It's y plus 2 squared equals 1 plus something plus something. Now, what did we add to both these sides? Well, we had to multiply 3 to 1. That's 3. And we multiply 2 and 4. 8. So what this would be 3x minus 1 squared plus 2y plus 2 squared equals 1 plus 3 plus 8, which is 12. Now what we have to do now is to have these denominators down here, what we have to do is divide. So let's divide this by 3. That means everything gets divided by 3. That gives us x minus 1 squared plus 2/3 y plus 2 squared equals 4. Do the same thing, but this time for the value outside our y plus 2 squared. So let's divide everything by 2. Divide everything by 2. Divide everything by 2. 2 equals x minus 1 squared over 2. And this simplifies to 1/3, right? So this would just be y plus 2 squared. All right, so we're really close now, but we have our value 2 here, right? So we want to get this to 1, as it has up here. So we divide everything by 2 again. That gives us x minus 1 squared over 4 plus y plus 2 squared over 6 equals 1. So with that, we know because this value is larger, we know that this is actually our semi-major axis. It's the larger of the two. So we know that 6 equals b squared. Remember, b is our semi-major axis, meaning that it's only half of it. So let's square root both sides to get b. b equals radical 6. But we want 2b, which is our our major axis. Just our major axis. So 2 times radical 6 is 2 rad 6. And that gives us our final answer, which is answer choice E. In 25, we have a point with rectangular coordinates 3, 4 and polar coordinates 5 theta, and it's asking us for the value of theta. Well, it's given to us that r equals 5, and we can confirm this by drawing this out quickly. We have our triangle with x equals 3 and y equals 4. I said it was a triangle because we can just quickly get the length of our r just by identifying that this is indeed a 3, 4, 5 right triangle. And what it's asking us 4 is this length over here. And to quickly get that, the formula to get it is, since we're given the opposite and adjacent, is just the inverse tangent of, because in SOHCAHTOA it's opposite over adjacent, it's 4 over 3. And doing that, we get 53 degrees, 53.13. And thus, in this case, it's answer choice D. Alrighty, for 26, we have PQ is called a lattice point if P and Q are both integers. How many lattice points lie in the area between the two curves x squared plus y squared equals 9 and x squared plus y squared minus 6x plus 5 equals 0? So what is this question asking? Well, it's asking us, really, how many coordinate points are in the intersection of these two curves? So let's graph this out on our calculators. So our calculators will show us two circles, a larger one and a smaller one. And all this question is asking us for is to find how many integer coordinate values are in this common area between the two. Well, just by looking at the graph on our calculators, we know that these coordinate points are 1, 1, 1, 0, and 1, negative 1. So the answer here is 3 lattice points. 27 asks us for the length of the lattice rectum of the hyperbola whose equation is x squared minus 4y squared equals 16. Now we want to get this in the form that we're familiar with, which is x squared over a squared minus y squared over b squared equals 1. Now this isn't too difficult. We don't have to complete the square or anything, it looks like. If we were to just divide both sides by 16 to get that right term to 1, we get x squared over 16, which is 4 squared, minus 4 over 16, which is 1/4. So this is y squared over 4 equals 1. So we have our center form for our hyperbola already. So it tells us what's our lattice rectum. Lattice rectum formula we discussed earlier is 2b squared over a. That's the length of our lattice rectum. So we have b, 4 equals our b squared. 4 equals b squared. So what's b? b equals 2. In this case, you have a. So 16 equals our a squared. A equals 4. Let's plug that in. 2 times 2 squared over 4. So these two cancel out. We get the length of our lattice rectum is 2.
Our final topic for this review is data analysis, statistics, and probability. So let's review a couple of these concepts first, okay? So we'll start in the left box. We're going to talk about mean, median, mode, and range. The mean, okay, the mean is simply the average of the numbers in a data set, okay? And what that looks like is basically the sum of the terms in the data set, sum of all the terms, divided by the number of terms, okay? The median, there's something very important to pay attention to here, is the middle value of a sorted, okay, of a sorted set of data, right? So for instance, if we go, this is an example here, if we have 1, 2, 3, okay, that's sorted, the middle value is 2, okay? Now you might be in a situation where you have something like 1, 2, 3, and 4, and the middle value here is sort of non-existent, right? It is conventional here to take the median as the average of these two numbers, right? So that the rightmost number of this left set here, the rightmost number, and the leftmost number of this right set here, okay? So just to review now here, a mode is simply the value, okay, value that appears the most. Value that appears most in a data set. So this, you could have multiple modes. It might be a multimodal data set. So you might have 1, 1, 1, 2, 3. So that one, the mode is 1. Or you might have something like 1, 1, 1, 2, 2, 2, and 3, in which 1 and 2 are both modes. Okay. And finally, we have a range of a data set. Okay. That's just the difference of the largest value minus the smallest value. Okay, the next thing we're going to review is the inner quartile range. Now, if you remember how to do a box and whisker plot, I'm just going to show this so we can get an idea, right? It usually looks something like this, where let's say you have a median here, okay, and then some min value and some max value. This is the median. We defined that before. And then this is the first quartile, and this is the third quartile, okay? The interquartile range, then, is represented by the length of this box. That's the IQR, okay? I'm going to call it that for short. So in order to find what that is, let's just do an example just to understand what that concept is. So we'll have the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay. We know there's, if we split it right down here, there will be 5 numbers on the left, 5 on the right, and it's sorted. So the median here is 5.5. Okay, that's the median, 5.5. Now, when we look at just the left set here, okay, this is the median of that subset. Okay, this is our first quartile. Likewise, on our right subset, 8 is the median of that right subset. That's our third quartile. The interquartile range, then, okay, is simply just taking that third quartile and subtracting the first quartile, right? So in our case, we have 8 minus 3 equals 5. So that is our interquartile range. Now, there's also a convention that's often used in mathematics, in which we take that interquartile range, okay, we multiply it by 1.5, okay? So in our case, we'll just kind of follow through with the example. So we'll have 5 times 1.5, which is 7.5, okay? And now I'm going to draw this interquartile range again, this box basically over here, okay? From that first quartile, this is the first quartile, if we go 7.5 in that direction, or the third quartile, and go 7.5 in this direction, that will tell us what our range is before we start counting certain data points as outliers, okay? So for instance, our third quartile here was 8, so this was 8 here, plus 7.5 would have given me 15.5. So if I have a data set, if I had, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 20, let's say this was a 20, okay? You can use this IQR times 1.5 rule and going either left or right, okay, to figure out whether that's an outlier or not. And finally, we'll talk about probability on this page, okay? So the most basic definition of it is the probability of something happening, okay, is the number of desired outcomes, okay, so what we want to happen, over the number of total outcomes, okay? So as an example, I'll put very small over here on the side. As an example, if we're rolling a 6-sided die, right, we can get either a 1, 2, 3, 4, 5, or 6, I'm assuming it's fair. And if the question asks, what's the probability if you roll that one die that you get a 6? Well, there's 6 possible outcomes, right? When you roll that die, you can get either a 1, 2, 3, 4, 5, or 6. And the desired outcome is the 6. Okay, so the probability of getting a 6, I'll use this notation here, would simply be 1, because there's only one possible outcome. There's that 1/6 that we want, okay, divided by all total outcomes, which is 6 total outcomes. That's 1/6. So we can extrapolate this a little further. So let's say we have some event A, right? Okay, that's of something happening. For instance, getting a 6 on a dice roll, right? So the probability of A happening okay, is 1/6 in our case. It equals 1/6. Now, it's also important to know what is the probability of something not happening, right? So we can just say P of not A, okay? And that's simply because probability, you have to add all your outcomes, right? Everything has to add up to 100%, okay? So the probability of not A has to be 1 minus 1/6, or in our case, more generally, 1 minus the probability of A happening, okay? And finally, if we have something, let's say 2 events, okay, what's the probability of A and B happening? As long as they are independent, okay, independent, and mutually exclusive, okay. So what this means, let me finish writing it out and then I'll talk about what this means. This is, you could just do probability of A times the probability of B happening alone, okay. Let's just talk about these terms real quick. Independent means if A happens, okay, it doesn't affect the likelihood of B happening, okay? So whether one happens or not doesn't affect the other. It's really independent of each other. Mutually exclusive simply kind of refers to they can't happen together, right? So you can't have I apologize. This should say, I'm going to add a caret here. This should say not mutually exclusive, right? We want both of them to happen at the same time. So if it were mutually exclusive, I'll correct myself here. If it were mutually exclusive, A and B cannot simultaneously happen, okay? So for instance, you cannot both be in 9th grade and in 12th grade, right? That's mutually exclusive. What grade you're in is mutually exclusive. So here, the 2 rules that we need to be able to multiply with this formula is that A and B, those 2 events, are independent and not mutually exclusive. So next we'll cover permutations and combinations and least square regression. So in permutation and combinations, this is sort of a way of counting, okay? It's a way of counting. And the most important thing is to be able to distinguish the difference between both so you know which one to use. Your calculator can do both, by the way, or you could use these formulas, which we'll go over in a second. So for a permutation, order matters, and we'll talk about what that means in 1 second. And for a combination, it doesn't matter. Order does not matter. Okay. What's an example of this? So for a permutation, the best example we have here is, let's say you have a race, okay? And who comes first, second, third place? Okay. In a combination, it might just be select a team of 3 students or something. So to be clear, in a permutation, let's say we have 5 students. We have students A, B, C, D, E. Okay. Let's say we're trying to figure out how many ways can they come in first, second, and third place, right? So you could have, for instance, ABC. You might have BCA, and so on. There's so many to do here. You got to note that when A is the first one here and B is the first one, that's not the same. They might both have ABC in it, right? So this is BCA. They have the same individuals in it, but the order that they come in matters. Okay, like each one of those counts as a distinct set of possible permutations. On the other hand, a combination order does not matter. So once again, we'll say we have students A, B, C, D, E, but let's say we said select a team of 3 students, okay? So on your team, if you had students A, B, and C, and then, you know, another option is, again, let's try that BCA, effectively, don't you have the same team here, right? They're the same 3 students. It should not be counted multiple times. Any combination of having students A, B, or C in whatever order is the same group of the 3 students, right? So those should not be counted twice or 3 times or however many times, right? Because there could still be CBA, CAB, BAC, ACB. So there's multiple ways to write these but have the same students. So that takes that into account and removes those duplicates. So in our case here, just to use them as an example, these 2 situations as an example, let's use the formulas here. The number of permutation of n things. So that just means this NPN here is just n things taken n things at a time, so all n things. And that's just a how would you, let's say we ran this race, right? And how many ways could they come in first, second, third, fourth, fifth place? And that's simply 5 factorial, okay? And you can just simply put that in your calculator. Again, factorial is just 5 times 4 times 3 times 2 times 1, all the way till you get to 1. There's 120 ways to organize that race, right? So that they come in all these different orders. Okay, so that's the first one. The second one is permutations of n things taken r at a time. In our case, we're doing, so NPR, we're going to say 5 students taken 3 at a time, right? And that's how many ways can they come in first, second, third place. That was our example here that we wrote in black, right? So we can use the formula that they gave us, that's 5 factorial over 5 minus 3 factorial, okay? So it's basically 120, which we had before, divided by 2, so that's 60. And so there's 60 ways that these 3 students can come in first, second, and third place. Sorry, these 5 students can come in first, second, and third place. And then the final one here is n things taken r at a time, but this is a combination, okay? The combination of things, so NCR would be 5C3 equals, same thing, 5 factorial over 5 minus 3 factorial, and an extra 3 factorial here. That will leave us with 10. So you see the difference here. We go from 120, which means just how many ways are there to organize 5 students into first place, second place, third, fourth, and fifth place. Then we say how many ways are there to take those same 5 students and put them in just places 1, 2, and 3. Okay. And then the final one here is how do you take those students and just put them on a team of 3? And there's significantly less or fewer ways to do that. Again, because we're removing all the duplicates. Okay, so that is permutations and combinations. And this next topic here is least squares regression. And you might not see this topic super often on the exam, but it's good to at least have an idea of it and how your calculator might be able to help you with it. So sometimes you're given some sort of graph, and let's say it looks something like this, and there's a bunch of data points. Okay, something like this. And just as an example, we can say this is the age of a person or maybe a student, and maybe this on the side here is their height in, let's say, centimeters, right? And basically, you can kind of tell right now that maybe as this person's age increases, or as any individual's age increases, it looks like their height is increasing as well. The idea of least squares regression, or specifically a linear regression here in our case, linear, is being able to draw a line through our data points, okay, so that the difference, when you add up the kind of these squares here, when you square the errors from the line to the actual data point, we've minimized it. That's kind of what it does. Now, you don't have to know really all the ins and outs. It's just a line that goes through it that tries to approximate that data. Now, there's multiple types of regressions, right? This is a least squares linear regression. It also exists for quadratic as well, and maybe even exponential and other things. So you should be familiar on your calculator if that does come up, but those should be functions that are available on your calculator. But when you do a least squares regression on your calculator, typically you put it in some sort of spreadsheet or list, okay? Spreadsheet or list, there we go. It differs on each calculator, so I won't do a demo here, but some sort of spreadsheet or list where there's the x values, in our case the age and the corresponding height, right? So let's say, age 5, maybe 130 centimeters or something, age 6, maybe 131, and so on. I'm not sure if those are actually accurate, but just for the sake of this example. And then usually you'd have to do some sort of analysis on it to make it spit out a linear regression. And usually that linear regression gives you an R value, or a kind of a coefficient, correlation coefficient. usually represented by r, and it can range from -1 to 1. 1 is a perfect correlation that's positive, so the line basically fits directly through your points as a straight line, like this. Okay. A -1 would look just pretty much the opposite. Still a straight line, perfect correlation, but it's negative. Okay. And then usually, as part of the linear regression, it gives you the equation of the line, of course. So it'll usually give you the m, that's the slope, right? It'll give you b, which is the intercept. And then when you graph it, you get, here's b, here's the intercept, and you can just graph the slope. So again, not much we can really talk about here unless there's a question that comes up. But again, you probably won't see this super often, but still very helpful to know how to do it on your calculator. Okay, in this next question, we're being asked that at the end of a meeting, all participants shook hands with each other. 28 handshakes were exchanged. How many people were at the meeting? So we should be able to recognize very quickly that this is a combinations type of question. Okay. Right, because the order doesn't matter. If there's, let's say, we don't know how many people there are right now, but let's say there's, person 1 and person 2, they can only shake each other's hand once, right? Everyone does it once with each other. If 1 shakes 2, it's the same as 2 shaking 1. It's kind of the same interaction, right? So effectively, this is a something, we don't know how many, choose 2. Okay, so this is the combination notation we know. Okay, and that equals n factorial, in our case x here, this is n, right? It's n choose r, okay? N factorial all over n minus r factorial r factorial, okay? So that's the notation in our case. Now, it's pretty easy here to just use your calculator, okay? And you can either plug it into this formula, or if your calculator has the capability, or if you know how to use it, there is this form. At least there is on my TI Inspire CX cast. Okay, so if you plug these in, you will find that 8 is the correct answer, okay? And we can quickly just work on that. So that's 8C2. We find here that 8 factorial over 8 minus 2 factorial times 2 factorial. If we work this out, okay, we have 8 factorial, which is 40,320, right? We're going to divide that by, this is 6 factorial here, okay? So 6, that's 720 times 2 factorial, and that's just 2, okay? When we take these numbers, 40,320 divided by 720 divided by 2, we get to the answer we want, and that is 28, and that's 28 handshakes. All right. In a group of 30 students, 20 take French, 15 take Spanish, and 5 take neither language. How many students take both French and Spanish? So let's remember we have an entire group of students here. That's only 30. Okay, we can tell if we just add all these up, that's going to be 40, and that tells us there's going to be some duplicate, right? Maybe there's people taking both French and Spanish, right? That's what it's asking us, of course. So it's saying, if we just drew a Venn diagram here just to see everything together, 20 take French, so there's 20 in this entire circle, that's including the overlap. There's 15 taking Spanish, and there's 5 out here taking none, okay? It's 5 taking none. So let's just think about this real quick. If there's 5 taking none and there are 30 total, okay, the students taking languages should total to 25. Okay, so that's French only, we'll write it this way, French only plus Spanish only plus French and Spanish should equal 25. Okay, so we're being told there's 20 French, okay, there's 20 French taking students, there's 15 taking Spanish, but there's some overlap in between. There's this overlap here, okay? We could just call that, for now we'll call it X. We don't know what that overlap is. So currently, what they say here, this 20 is actually equal to French only plus X. Likewise, this 15 in Spanish is Spanish only plus x will equal 15. Okay? So now we can try to quickly solve for what that overlap is, because we know it has to equal 25. Okay? That overlap x is F and S, right? F and S together, French and Spanish together. So let's see if we can plug in. So F only is going to go into here. That's 20 minus x, okay? Plus S only is 15 minus x, plus x should equal 25, okay? Again, x is the intersection between. So we can cancel one of the x's, and we're simply left with 20 minus x plus 15 equals 25, okay? And just subtracting 15 on both sides, okay? Actually, I'll come up here to get some more space. Subtracting 15 on both sides, we have 20 minus x, okay, equals 10. Okay, I could subtract 10 from both sides, add x to both sides. Minus 10, and plus x. It cancels out, okay? This cancels out. So we'll be left with 10 equals x. And like we said, x is representing how many students take both French and Spanish. So our answer here is choice C. All right, this is our last question. Of the following list of numbers, which has the largest standard deviation? So when you hear the word standard deviation, you should be thinking how spread out is the data, okay? The more spread out it is, the larger standard deviation we have. Now there is a formula, and you can actually calculate the exact standard deviation if you wanted to. And there's ways to do that in your calculator, so it would be good to be familiar with that to double check answers, etc. But here's how we're going to do it here today. We're just going to look at the choices and kind of do it from observation, okay? I'm going to start down here because this is really interesting. 11, 11, 11. To me, if we're using this how spread out data definition, that is not spread out at all, right? All three numbers in our data set are the same. So that has 0 standard deviation, right? So we don't like that as an answer. All right, let's look here. The mean will be 11, that's like right in the middle. And it's 10, 11, 12. They're just numbers next to each other. So I'm just thinking, okay, they're all 1 away from each other. We could keep that there for a second. Here's choice C, 5, 7, and 12. Well, to me, that's a little more spread out, right? 5, just, if we do it on a number line here. Here's 7, here's 5, and way out here is 12. So that's actually more spread out than D. Okay, let me write out. So this would be D, this is C. D is pretty much here, 10, 11, 12, right? That's not very spread out. C is more spread out, so I like C better right now. We'll cross out D. Let's check choice B here. Choice B goes a little bit longer on the number line. We're going 3, which is way down here, 7, and 14, okay? Yeah, this is just eyeballing it. You can tell this is going to be more spread out than choice C. Right, so we can eliminate choice C. So right now our best option so far is choice B. And finally we have choice A, which is very, very similar to choice B. It has a shared 7, but we notice it has a 2 and a 15. So 2 is down here, that's less than 3, right? So 2 is down here. 15 is greater than 14, okay? So if you look at it, the spread of that data is just larger, just a bit larger, right, than choice B's. So from that, we can choose answer A. Answer A has the largest standard deviation. So this concludes our SAT Subject Test Math Level 2 review, and we would like to thank you guys for listening and wish you the best of luck on your exam.